Welcome to my talk about DNA Deformable Articulations Network for Dynamic 3D Human Reconstruction from RGB-D video. And I am Khoa. This is the joint work with Trong, Thang, Pham, Kashu, Yamazaki, Minh, Trong, and Ngan from University of Arkansas. We are proposing a framework to reconstruct a 3D human mesh of a non-rigidly moving human captured by an RGB-D video. Now, let's briefly review the previous related work. One of the most effective ways to reconstruct the human mesh is to use a template. Previously, there are several successful methods to reconstruct the human head and the human body. However, these methods require us to redesign a template for every category of the human, for example, the head, the upper body, the full body, or the gender. To overcome such limitation, the frame-by-frame methods sequentially resolve the motion and reconstruct the object through every frame. However, the errors can accumulate through time, and these methods cannot remove the error in the middle of the reconstruction. Finally, the nerve-based methods can resolve the accumulated errors by training the nerve models at a global view. Although achieving very good results in short videos, but because these methods train the network on RGB input, they meet the problem of ambiguous 2D, 3D relationship and get a very bad result on longer video. We propose the Deformable Articulations Network, which will try to resolve the deformation via the articulations that is figured out per every input video and completely template-free. Secondly, we model the 3D human shape globally to avoid the errors accumulation. And finally, our model operates on the RGB-D input to remove the ambiguous 2D to 3D relationship. Given an RGB-D frame, we first convert it into a color point cloud, and then we build an occupancy grid from that point cloud. The occupancy grid will be fed into a Neural Articulation Prediction Network, which is NAPNet in short, to estimate the articulated bones that model the human movement at that frame. Given an observed point xt and the estimated bones at frame t, we project it into the canonical space as x-tutor. The position of the x-tutor will be fed into the SDF-Net to predict the SDF value at that position, and also the color net to predict the color at that point. The SDF is crucial to define the 3D human mesh at that frame. Given another frame J, we also do the same thing to obtain the estimated bones of frame J. Then, using the estimated bones at frame J, we can project x-tutor into the corresponding position at frame J, and then this position will be used to compute the deformation loss to enhance the temporal consistency of the predicted bones throughout the video. The deformation loss will be explained later in the next slide. Here are the losses to train our model per every input video. The surface losses constrain the point sampled on the observed surface at every frame. Geometric loss constrain that the predicted SDF value of these points should be close to 0. The color loss constrain that the predicted color should be close to the observed color. And finally, the visible loss constrain that the predicted normal of the points should face to the camera view. Next, the near surface losses put the constraint on the point sample near the observed surface. The regularization loss constrain the points to follow econal theory. The coverage loss constrain that the points outside of the surface should have the positive SDF, and the points inside of the surface should have a negative SDF. The cycle loss constrain that if we project a point into the canonical space and project it back to its frame, the new position will be close to the original position. Finally, we design an easy-to-hard geometric-based deformation loss. Concretely, if we project a point from frame T to frame J, and it is still observable by the camera view of frame J, then we return the chamfer distance of the projected point to the observed point cloud FMJ. T and J are at first sampled as nearby frames, and then we gradually increase the distance of T and J, so at the end of the training, T and J can be up to 30 frames apart. To evaluate the effectiveness of our proposed method, we compare it with the state-of-the-art methods on the DeepDeform dataset. Out of 20 videos of human, we picked 5 videos of 5 distinct subjects, and the matrix we use to compare is the geometric error in the centimeters. To train our network, we used one single GPU of 48 gigs, and for every video we train the model on 12 hours, and the root pose initialization is done by a pre-trained ResNet 34 that is trained on a synthetic human mesh. The quantitative results show that our proposed network outperforms all of the previous state-of-the-art on 4 videos and is competitive with the most recent work on 1 video. And here are the qualitative comparisons. As we can see, our model can achieve much higher fidelity to reconstructed mesh compared to previous state-of-the-art. Here is another visualization of the estimated bonds and the reconstructed mesh. To conclude, our proposed Deformable Articulations Network can achieve high-quality dynamic human reconstruction. It incorporates color and depth streams to remove the 2D ambiguity, and it effectively captures the motion by the learned articulated deformation. Thank you very much for watching my video, and I hope you will have a great day.